Good evening, Sandy. This is the ABC of stellar evolution. As the subtitle says, I'm going to be looking at the birth, the life, and the death of stars. So when we look into the universe and we see galaxies, actually galaxies contain a lot more than just stars. They contain a huge amount of gas and dust as well, but it's the stars we tend to think about in terms of trying to understand how the universe is put together. So let's have a look at what the categories are of the contents that I'll be dealing with. I'll be looking at what's going on in the core of a star, the nuclear fusion. I'm not going to turn it into a physics lesson, don't worry. We'll look at how stars come to be, and we'll think about the way stars live their lives, the balance between radiation and gravity. We'll look at how different star types have different lives. Some of the massive ones live fast and die young, for instance. And we'll ask what happens when stars come towards the end of their lives. And when stars do die, do they go with a bang or with a whimper? And what's left afterwards once a star has died? And we'll just finish with thinking about when gravity wins, a star may become a black hole. So let's just remind ourselves of where we are in the life cycle of the Sun. If we look at a timeline here, starting on the left at the Big Bang, I'm not going to be talking about how the universe came to be. That's a completely different talk. But if we think about the Big Bang on the left and where we are now, 13.8 billion years later, we think the Sun came into existence at about the time indicated there, some 9 or maybe 10 billion years after the Big Bang. And so the Sun is now approximately middle-aged. It's been around for about 5 billion years, and it'll be around for another 5 billion years, at which point it will start to change. It will start to grow into a red giant phase, and once it's lost the outer atmosphere, we'll be left with a white dwarf. So these cartoons here, not to be taken to scale. This is just an indication of what is in store for the Sun, and we'll have a look at why that happens in due course. So what's going on in the core of a star? The pressure and temperature conditions are just right, in other words, high pressure and high temperature, to fuse hydrogen into helium. So what's happening is protons are being fused together. This little cartoon indicates that 4 protons fuse together. It's not quite that simple because you'll never get 4 protons in the same place at the same time. It's a process whereby 2 protons fuse together and then they fuse with another one and then they get together and ultimately they produce the nucleus of a helium atom, 2 protons and 2 neutrons. So the net result is, if you start with 4 hydrogen nuclei, you'll end up with 1 helium nucleus. And the amount of mass that's lost in the process is indicated at the bottom. In any given second, 620 million tons of hydrogen is converted into 616 million tons of helium in our Sun. Those 4 million tons that have been lost through E equals mc squared, those 4 million tons are converted to energy, and that's how the Sun is able to produce the light and the heat that keeps most of the solar system warm. So stars are not simply nature's way of lighting up the universe, though we think of them basically as points of light in our night sky. As a physicist, we tend to think of them as fusion factories because they are the way that elements are made. Hydrogen was made in the Big Bang, and ever since the Big Bang, stars have been taking hydrogen and fusing them into heavier and heavier elements. We could ask, but how did the hydrogen come into existence in the first place? A very good question, of course, but not the subject of this particular talk. We're simply going to assume that the universe is full of hydrogen, and we're looking at how that hydrogen is used by stars to make heavier elements, and in the process release energy. So where do stars come from? Well, you could argue that making a star is actually quite easy. If you start with a big cloud of hydrogen, in fact, if you start with a big enough cloud of hydrogen, then the remaining steps are straightforward. Step 2 is you wait. Step 3 is you wait a little longer. Step 4 is wait just a little bit longer, and then you have a star. In other words, if you start with a large enough cloud of hydrogen, you need to do nothing other than step back and wait, and then you will make a star. Gravity will simply condense that cloud and ultimately produce nuclear fusion when the pressure and temperature are high enough. So in other words, any nebula like this, the Great Nebula in Orion, any nebula like this is effectively a star nursery, because somewhere near the core it's dense enough and hot enough for stars to be born. So what is it that actually triggers star formation in the first place? Well, we know there are large clouds of hydrogen, so-called giant molecular clouds, floating around the galaxy, and presumably pretty much every other galaxy. Why are they called giant molecular clouds? Well, the clue's in the title. They look like clouds, they consist of hydrogen molecules, and they're big. And by big, I mean not just a few light years across, but they could in principle be hundreds of light years across. So huge compared to what we now understand as typical distance between stars. Remember, the distance from us to the nearest star is a few light years. So what makes a giant molecular cloud collapse? Well, there are a number of different triggers that can start the process. One cloud floating into another, colliding with another. Shock waves rippling through a cloud. How would a shock wave be generated? Well, for instance, a star coming to the end of its life as a supernova. We haven't quite got there yet, but we'll be mentioning that again later. A star coming to the end of its life could trigger new star formation in a giant molecular cloud. And another way the cloud could collapse is through galaxy collisions. And that sounds rather dramatic, to think about one galaxy colliding with another, but we think that happens quite often. This particular galaxy appears to be isolated, but if you look at the little pink dots that we see everywhere, these are characteristic of clouds of hydrogen. Hydrogen tends to glow at the red end of the spectrum, so in images like this, anything that looks like a little fuzzy pink blob is a hydrogen cloud, a star nursery. And when we see images like this, the Whirlpool Nebula, we perhaps notice that the perturbation, the disruption caused by this satellite galaxy on the right, is producing quite a lot of star formation. Whenever you disrupt the normal operation of a galaxy, whenever you produce ripples in these clouds, you can quite often trigger new star formation. We see that in particular in galaxy collisions. Here, for instance, the Antenna Galaxy. The tidal tails here are produced by the interaction of these two galaxies. If we zoom in and have a look in detail from the Hubble Space Telescope, we notice that there's a huge amount of star formation, an awful lot of pink and a lot of dust as well in the region where these two galaxies are colliding with each other. Collisions are almost inevitable in all galaxy evolution, and the Andromeda Galaxy, which is relatively close to us, only 2.5 million light years away, is close enough that gravitationally we are pulling on each other.
In progress.
They are pulling on each other. Let me just dismiss that. They are pulling on each other, and the two galaxies are going to pass through each other on a timescale of many billions of years. They'll pass through each other. Very few stars will actually collide with each other. And then the two galaxies will slowly, over the next 500 million years or so, merge together into one large galaxy. Individual stars are unlikely to collide with each other, but all of the gas and all of the dust in one galaxy is going to collide with the other, and it's that collision of the gas and the dust that leads to new star formation. So if we think about what that's going to look like from our perspective in the Milky Way, there's the Andromeda Galaxy as it stands at the moment, a small galaxy in the distance. Well, small, it's larger than the full moon as seen on our sky, but if we wait a little while, as it comes towards us, it'll grow in our sky. Here's what it will look like in 1 billion years or so. And in 3.5 billion years, it'll fill a substantial part of our sky. And as Andromeda passes through the Milky Way, there will be a riot of new star formation. The entire sky will be lit up with various clouds being triggered into new star formation. Now, this looks like a simulation perhaps of what a star is doing. In this particular case, no, this happens to be a large cloud of hydrogen. It's a computer simulation, and computers like to start with things with high symmetry. For instance, a spherical cloud. It's not very likely that a cloud of hydrogen is actually spherical, but it's easier to model that in the computer. So this particular simulation is starting with a very large cloud, perhaps 100 light years or so in diameter. There are very small variations in density and the motion of the individual atoms in this cloud. And then the simulation is going to let gravity do its stuff and sees what happens to all of the hydrogen atoms in the cloud. So let's run the simulation to see what happens. Some parts of the cloud seem to be moving outwards, but most of the cloud is collapsing inwards. And the brighter colours here correspond to hotter and denser parts of the cloud. So you can see that the inner part of the cloud is starting to collapse, and certain regions of the cloud are getting very hot. Eventually, that heat will undergo nuclear fusion and the hydrogen will be fused to helium and release energy. In other words, stars will be born. Each white dot here is a new star being born out of this collapsing hydrogen cloud. Notice that it looks almost like a popcorn machine here. We're not simply making half a dozen stars, we are making hundreds, if not thousands of stars in a star cluster. Notice that a lot of them are hanging around close to where they were born, but every once in a while you might notice one star goes flying off, because when the stars are born, they can be ejected out of the gravitational influence of all of the other stars and the hydrogen cloud itself. If we back off a little bit and do a little bit of a twirl, we see that the original relatively spherical cloud of hydrogen now looks very irregular. Not all of the hydrogen has been used up. Notice that although we've made perhaps thousands of stars, there's still some hydrogen left in the cloud itself, even though a fair bit has been depleted. So this is a simulation saying if you collapse a hydrogen cloud, you end up with a lot of stars being born. The question is this a reasonable simulation? Is this a reasonable facsimile of how we think star clusters actually look? Well, yes, that's a real star cluster, and it does bear a resemblance to the simulation that we've just seen. So we have some confidence that our ideas behind collapsing clouds of hydrogen do indeed give rise to star clusters such as this. Our own sun was probably born in a star cluster like this, but just like some of the stars we saw a moment ago, it looks like our sun was ejected from the star cluster, and because that happened billions of years ago, we have no idea which particular star cluster our sun was born in. But many of the stars that appear to be isolated were probably born together with a lot of siblings, but they've simply been separated at birth. When we think about what's going on inside stars, it's always a question of balance. Gravity is always pulling in on all the mass of a star, trying to contract the star. But because we've got thermonuclear reactions at the core, fusing hydrogen into helium or possibly heavier elements, there is energy being generated in the core, and that produces radiation which effectively pushes outwards. So gravity is pulling in, radiation is pushing out. And all stars are a balance between these opposing forces of gravity and radiation pressure. When those opposing forces are balanced, the star is happy, the star is stable. But if, for any reason, those forces become out of balance, then the star must change. The star must evolve. And many aspects of star birth and star life and star death can be explained in terms of this balance of forces and what I like to think of as the ABC of stellar evolution. So what are the A and the B and the C? Well, when we start talking about fusing hydrogen, or the nucleus of a hydrogen atom is just a proton, positively charged. If we want to fuse them together, because like charges repel, we have to overcome that repulsion before we can get them close enough to fuse together. And if we want to get them close, we need to have a lot of temperature and a lot of pressure to fuse protons to make heavier elements. So high temperature and high pressure will accelerate the fusion process. That's the A of the ABC. we've already seen what the B is. The B is the fact that all stars are a question of balance. A star is in equilibrium if gravity and radiation forces are in balance. And the final element of the ABC is C for compression, because we all know that compression produces heat. We know that whenever we try and pump up a bicycle tyre, what happens when you compress the air and put it inside a bicycle tyre? The pump gets hot, because compressing any gas, any fluid, it doesn't matter whether it's air in a tyre or the fluid in a star, when you compress fluids, they get hot. So there's the A and the B and the C. We'll see how they work momentarily. It's worth reminding ourselves that whenever we're looking at stellar evolution, it's useful to be able to classify stars according to their luminosity on the vertical scale of this graph and their colour or their temperature, their surface temperature, as indicated by the horizontal scale. Notice the horizontal scale sort of goes backwards. By convention, the cooler stars are on the right and the hotter surface temperature stars are on the left. And the colours indicate the approximate colours of the star. So there's our sun in the middle. We measure luminosity by the luminosity compared to how much brightness the sun produces, the total energy output of the sun. So by definition, the luminosity of our sun is 1 in those units. And the surface temperature of our sun is a little shy of 6,000 Kelvin. And we're going to refer back to this when we think of other types of stars. So what happens to different stars will depend on their mass. At least the mass is the principal factor that determines the lifestyle of a star. High mass stars, meaning stars significantly more massive than our sun, you might think that they have a lot of fuel because they're very massive, so surely that means they live a long time. Well, actually, it's counterintuitive. Because the gravitational forces are so strong in high mass stars, then the balance requires a lot of radiation to be generated in the core in order to withstand the large pull of gravity. And that means the nuclear fuel must be used up at a really fast rate in order to balance gravity. So rather than living for billions of years, as our sun will do, high mass stars might only live for a few million years. That might still sound like a lot, but remember, if a star only lives for 1 million years, then any planets going around that star, you could argue, simply won't have time, for instance, to produce any life, because life takes time to develop. What about low mass stars? And here we're talking about mass significantly less than the mass of our sun. Our sun, in all intents and purposes, is effectively an average mass star. If we think about a low mass star, then again, naively, we might assume that it hasn't got much fuel, so it's not going to last long. But actually, because the gravitational forces are relatively weak in a low mass star, the radiation forces required in the core don't have to be very high to maintain a balance. And hence, the nuclear fuel actually lasts for a long, long time. For a star, for instance, with a mass of only 10% of the sun, we're not even sure what happens when the fuel runs out, because for most of these low mass stars it hasn't actually happened yet. Low mass stars might live for trillions of years, much, much longer than our sun. Much longer than, indeed, the history of the universe. Before we go any further and look at how the ABC helps us understand evolution, let's just take a little detour and remind ourselves that masses can vary from stars that are 10 times smaller than the mass of our sun, or 10 times larger, maybe more than that. They could conceivably be 100 times smaller or 100 times more massive, but that's pretty much the limit. We can't really imagine mass varying by much more than that relative to our sun. But in terms of the size, in terms of the radius of a star or the diameter of a star, they can change much more dramatically than merely 1 or 2 orders of magnitude either side of the sun. So let's just take a little aside and remind us how the size can vary between stars. Let's give ourselves a sense of scale by reminding ourselves of the size of planets in the solar system. These are not in order of distance from the Sun. They're in order of size, Mercury to Earth. Let's take the Earth on the right-hand side of that panel and put it on the left-hand side of the next panel. And now we see that Earth is quite small compared to the ice giants, Neptune and Uranus, and very small compared to the gas giants, Saturn and Jupiter. Jupiter, of course, the largest planet in the solar system. Let's play that same trick again. Let's take the Jupiter-sized object on the right-hand side of this panel and place it on the left-hand side of the next panel. So there we see Jupiter in the bottom left, and a relatively small star called Wolf 359 is sitting next to it. Notice that Wolf 359 is not that much bigger than Jupiter. It's one of the smallest stars that can exist. By comparison, the Sun, some 10 times larger in terms of diameter than Jupiter. And the Sun looks small compared to Sirius, the brightest star in our sky, of course, apart from the Sun itself. So there's Sirius looking something like twice as large as our Sun. But we're nowhere near finished with large stars yet. Let's take Sirius and do the same trick, put it on the left-hand side of the next panel. So now we see Sirius, the blue marble in the bottom left there, and next to that we see Pollux, then Arcturus, and then Aldebaran. So now we're getting into the realm of red giants, which ultimately will be the fate of our Sun in a few billion years. So clearly Aldebaran is absolutely huge compared to Sirius, which, remember, is rather larger than our Sun. But we're not done yet. Let's take Aldebaran and put it onto the left-hand side of the next panel. There's Aldebaran. Rigel is a fair bit bigger, but look at the size of Antares and Betelgeuse, supergiants. And you can see, remember, that the mass doesn't change that much between any set of stars that we're talking about. They can be less massive or more massive than the Sun, but if a star is really that big and its mass can't be that large, these stars must be considerably less dense on average than our Sun. And just to give us an idea of what the largest stars look like, let's take Betelgeuse and put that on the left-hand side. And we notice that it's by no means the largest. The actual largest star might change year on year as we discover new ones, but when this particular graphic was made, one of the largest stars around was called VY Canis Majoris on the right-hand side there, some twice as large as Betelgeuse. And because we've been changing the scale each time we've shown a new panel, let's just attempt to actually show the Sun to scale with the largest star that I've had in that panel, VY Canis Majoris. And if you're having difficulty seeing it, that's because I haven't brought it in yet. Let's bring it in so you can get an idea of the scale. And bear in mind that in this particular graphic, I have exaggerated slightly. I haven't exaggerated the size of VY Canis Majoris relative to the Sun. I've exaggerated the size of the Sun relative to VY Canis Majoris. In other words, the Sun ought not to be a little yellow dot there. If I put it its true size relative to this supergiant on the right, the Sun would barely be 1 pixel and might actually be invisible on your monitor. So you can see the variation in size is absolutely huge compared to the rather more modest variation in mass for various stars that we know. So what happens when the fuel runs out? Well, this is where the ABC of stellar evolution comes into its own, because we can use the A and the B and the C to figure out what's going to happen when the fuel starts to run out. If we think of a star like our Sun, when the hydrogen starts to run out at the core, well, if we're no longer burning fuel at the same rate, the radiation is going to drop. And remember, all stars are a balance between gravity pulling in and radiation pushing out. So if the radiation starts to drop, that means the star is going to get out of balance, because now gravity wins over radiation, because the radiation is now less than is required to overcome gravity. So if gravity wins over radiation, what's going to happen? The star is going to shrink. And if the star shrinks, compression produces heat. So the core is going to get hotter, which means it's now going to become not simply hot enough to fuse hydrogen. If the temperature goes up enough, it's going to capable of fusing heavier elements, for instance, fusing helium into heavier elements like carbon, for instance. So out of balance means compression, compression means a higher temperature, and a higher temperature means we're going to accelerate the fusion process and we're going to start fusing heavier elements. So after hydrogen comes helium. And when the core gets hot enough to fuse helium, more radiation is produced, and that increased radiation balances again the gravitational pull. And this process of fuel runs out, so it gets out of balance, the star shrinks, compression produces heat, the heat accelerates the fusion process, which brings the star back into balance. In principle, this can go on and on and on for heavier and heavier and heavier elements. A, B, C, A, B, C, A, B, C. If the star is heavy enough, this can happen for element after element after element. Our sun isn't particularly heavy, so our sun will run out once the helium has started burning. There will be no more heavier elements much after that. But the ABC allows us to understand the processes that occur. When we think about how much energy is released, again, I'm not going to convert this into a physics lesson, but if we think about how much energy is released as we fuse heavier and heavier elements, it just so happens that we get a lot of energy out of fusing hydrogen into helium. We get a little bit less when fusing helium into heavier elements like carbon, less still when we fuse carbon into heavier elements, all the way up to iron. And once we've gone beyond iron, notice this curve goes the other way. We don't get a release of energy. It takes energy to make heavier elements. So we can, inside stars, expect heavier and heavier elements to be made up to and including iron, but not beyond that. So we can ask ourselves, where do all the elements in the periodic table come from? If we just get rid of some of these garish colours, we know that hydrogen can be fused into helium, and ultimately helium in large enough stars can fuse into carbon and oxygen and a lot of the heavier elements that we're familiar with, like phosphorus and calcium and various elements that we are made of, all the way up to iron. But clearly, iron is only sort of halfway, if that, through the periodic table. We know there are lots of heavier elements here in the Earth's crust, like silver and gold and lead, for instance. So if they are not made by fusing elements in stars, how do we get those heavy elements? We have to think about how stars die. If we take a medium mass star, for instance, like the Sun, the gravity pulling down on the star may not be strong enough to hold on to the outer layers of the star when helium starts to burn. Remember, the hydrogen runs out, the star will compress, helium will get hotter and eventually start to burn or fuse into heavier elements, up to about carbon. And when that happens, if gravity is not strong enough, which it might not be for a star of the mass of our sun, then some of those outer layers can be lost. The star starts to swell up into a red giant, and some of those outer layers could be lost completely to the interstellar medium. As the star expands into a red giant, the outer layers start to cool, which is why the surface temperature drops and the sun's temperature will drop from something like 6,000 Kelvin to about half that, somewhere around 3,000 Kelvin. And red giants are in this part of the classification chart, luminosity versus surface temperature. There's the red giants. Remember where the sun was in the middle there? Red giants are cooler, so further to the right, but they have a much larger surface area, so although they're cooler, they are more luminous, so they are higher in this particular diagram, so top right of the sun. If the helium fusing becomes unstable, the outer layers are completely shrugged off, and that leads to the formation of a planetary nebula. Remember, that's nothing to do with planets. That just means the outer atmosphere of the star is detached from the star itself and becomes a nebula full of the elements that were originally inside the star. What's left is effectively what used to be the core of the star. Now the outer atmosphere is gone. You're left with the hot core of the star. No more nuclear fusion, but it's just a very hot lump of whatever elements are left. This is a white dwarf, perhaps about the size of the Earth. And white dwarfs are here in the bottom left part of the diagram. So they tend to be quite hot because they were originally the core of the sun, so much higher surface temperatures, so further over to the left. But they are relatively small, so a relatively small surface area, hence the luminosity somewhat lower than that of the sun. So you can see planetary nebula. You can understand perhaps from an image like this why they were originally called planetary nebula. Some planetary nebula are very spherical as the outer atmosphere of the sun is shrugged off into interstellar space, and some of them in a small telescope might give the appearance of a small planet. Various planetary nebula you might know about, like the Ring Nebula. This is a rather lovely one called the Helix Nebula in the constellation of Aquarius, visible low down in the south from England. That's actually a Hubble Space Telescope picture, but it's actually large enough in the night sky that you can actually image it. Here's a picture I took with a telephoto lens on a camera. So this is not taken with a telescope. So I would agree that the Hubble Space Telescope is a rather better image, but because it's a relatively large object in the night sky, you don't need a telescope. A telephoto lens on a camera will be enough to capture this particular object. So if you want to see a star that's come to the end of its life, have a look or have a photograph of a planetary nebula. What if the star is rather high mass? Well, if it's a high mass star, quite a few times the mass of our sun, then the gravity is stronger, which means the gravity will hold the star together through all stages of nuclear fusion, so-called nuclear burning. In other words, hydrogen will fuse into helium. If the mass is large enough, helium will fuse into carbon and then the heavier elements, neon and oxygen and silicon. And if the mass is really large, then all of those elements will fuse all the way up to iron. At the end of its life, when the iron core can no longer provide energy, remember you can't fuse iron into anything else to release energy. It'll always take energy in order to fuse iron beyond that into heavier elements. So when the star starts to form iron and its fuel is running out, the star collapses. Gravity effectively wins, and gravity pulls the outer layers of the star down, crushes the core, and an enormous rebound sends the rest of the star out into the interstellar medium. The core is crushed to the size of a few kilometers. Remember, a white dwarf was about the size of the Earth, but now we're talking about crushing the core down to only a few kilometers, barely the size of a city. The rebound of the shockwave ejects most of the mass of the star into interstellar space. And what we see is a supernova remnant. Here we can barely make out the original star. It is so small and so faint compared to the enormous size of the remainder of the star thrown into the interstellar medium. This, if you recognize it, is the Crab Nebula, Messier 1. The energy of a supernova is truly incredible. As a physicist, you can always work out on the back of an envelope how much energy does it take to rip a star completely apart. And you can calculate that it takes about 10 to the power 44 joules of energy, which means nothing unless you're a physicist, because you don't tend to think in terms of these units. But let's look at it another way. Imagine the total energy output of our sun. Our sun is not going to go supernova, but just for comparison, imagine the total amount of energy that the sun has been putting out, not the tiny fraction that the Earth receives, but remember the sun is emitting in all directions and we receive just a tiny fraction of that. Think about the total amount of energy that the sun has been producing, and in each and every second of its 5 billion year lifetime so far and the 5 billion years to come. If you add up the total amount of energy that the sun will have ever produced, That gives you an idea of what 10 to the 44 joules means. And remember, this energy is released not over a 10 billion year period. This energy is released in just effectively a few seconds. So the word explosion just isn't enough to grasp what we mean by a supernova. In the chaos of the supernova, nuclei fuse together. In other words, the supernova provides the energy to actually fuse iron into heavier elements. So essentially all the elements heavier than iron are generated during the supernova. And the supernova is also the mechanism by which all of the elements generated up to this point and any elements generated after this point, the death of the star is the mechanism by which all of these elements are ejected into interstellar space. So heavy metals found on the Earth were made in a supernova. So the Sun cannot have been made simply from a cloud of hydrogen. It must be a multi-generation star. In other words, it's not second generation, it probably is third, fourth, fifth, sixth, seventh, eighth generation. A star was born, it lived, it converted helium into heavier elements, and then it died. And then another star was born out of the remnants of that and lived its life, generated heavier elements, and then died. And then another star was born, etc. Generation upon generation of stars were born, lived, and died, probably billions of years ago, in order to seed our region of space, where the Sun ultimately was born, with the heavy elements that we see around us in the Earth's crust and elsewhere in the solar system. After a supernova has crushed the star's core and ripped apart everything else, what is left behind? Well, a star, depending on the mass of the original star, the star that's left might only be a few kilometers in diameter. A neutron star is one possibility. A neutron star, literally just 3 or 4 or 5 kilometers in size, perhaps up to about 10 kilometers or so. Very compact, a huge mass, perhaps a similar mass to our Sun. Huge mass, but only in a few kilometers. So enormous density. And because of the way the star collapsed, very large magnetic fields as well. If the star happens to be radiating, radio emissions will tend to be focused by the very strong magnetic fields in the directions of the poles of the star. If the magnetic poles are not aligned with the rotational poles, a bit like the Earth's axis, then as the star spins, we can get pulses of radio emission. For instance, here's a few examples where the radio emission has been converted to an audible pulse, so we can hear the so-called pulsars. We can hear the pulses coming in 800 milliseconds period, so a little more than one rotation per second. So we have something with the mass of our Sun rotating roughly once per second. The next pulsar rotates rather faster than that. This is the Vela pulsar with a rotation period of 89 milliseconds, rotating 10 times per second. Again, try and imagine something with the mass of our Sun rotating that fast. Faster still. So fast we can't hear the individual pulses, it sounds like a hum. 30 rotations per second from the pulsar in the Crab Nebula. Again, so fast we can't hear the individual pulses, rotating 5 millisecond period. And the fastest one we know? Okay, that's really irritating, I better stop that. One of the fastest pulsars we know has a period of about 1.5 milliseconds, rotating hundreds of times per second. And it's difficult to imagine anything rotating at that sort of speed. I say 1.5 milliseconds, but actually pulsars rotate so regularly we can use them to regulate our atomic clocks, because the rotation periods of some of these pulsars are more reliable than the fantastic accuracy we can get from atomic clocks. So that 1.5 milliseconds is only an approximation. The actual rotations period is 1.55780644887275 milliseconds. And yes, that is the genuine accuracy with which we can determine the rotation period of a pulsar like this. If we do this for hundreds of pulsars, we get a very accurate indication of what our atomic clocks are doing. Now, it's possible, if the star was massive enough, that rather than stopping by generating a neutron star, it's possible that the object that's left is even smaller than, let's say, a few kilometers. And once you crush an object with a mass similar to the mass of our sun down to a radius of smaller than about 3 kilometers or so, you're no longer generating a neutron star, you now have a black hole. There is nothing we know of that can stop the collapse. Once we get down to that sort of size, we don't know what's going on inside the event horizon of a black hole, the event horizon being the one-way valve, the one-way membrane, if you like. There's nothing physical about it, but once anything falls inside that radius, nothing can get out, not even light. The escape velocity is greater than the speed of light. So we don't know what's going on inside a black hole. It might continue collapsing down to nothing, but we really don't know. When a black hole forms, it's quite possible that an accretion disk forms around it. So the Event Horizon Telescope, a collection of radio telescopes, recently managed to image this donut that we can see here, is the accretion disk, matter that's, as it were, swirling around the black hole in much the same way that water leaving a bathtub won't go immediately down the plug hole. It tends to swirl around before going down the plug hole. An accretion disk is matter that's accreting around the black hole, waiting its turn to be pulled into the black hole itself. As matter circulates around the black hole, the matter is interacting with all of the other particles, atoms of matter in the accretion disk itself. The accretion disk gets very hot and emits electromagnetic waves, which is how we can pick them up by radio telescope. This particular image is of a black hole in the galaxy M87, Virgo, the Virgo cluster. And this supermassive black hole is thought to have a mass of 6.5 billion solar masses. We have a supermassive black hole at the centre of our own galaxy. That's the so-called Sagittarius A star. This particular supermassive black hole is 4 million solar masses. Now, I was describing what happens at the end of a star's life. The question is, how do these enormous black holes come to be? If we know that a star at the end of its life will produce a black hole with a mass of a few times the mass of our sun, how do we end up with a supermassive black hole with much higher masses? Do we start by having lots of stars that end their lives of black holes and then they eventually merge together? Or does a black hole come from the collapse of a very, very large cloud of hydrogen which collapses into a black hole in one go? Well, the answer is we don't really know, which is one of the reasons why the James Webb Space Telescope is looking back in time as early as possible to the first stars and the first galaxies, trying to see when did these supermassive black holes first come on the scene. Is it likely that stars started first and then supermassive black holes came later? Or is there evidence that supermassive black holes were there in the very early universe? At the moment, the jury is out. There's some tantalizing evidence that's starting to come in, but in the next few years, we'll have a much better idea as evidence from the James Webb Space Telescope continues to come in. So let me give a graphical summary of what I've been talking about. If we start with a cloud of hydrogen, that cloud of hydrogen under the influence of gravity can collapse into a star, let's say a star similar in mass to our sun, which will happily fuse hydrogen into helium for billions of years. And when the star comes to the end of its life, because it becomes out of balance, it'll start to swell up into a red giant. And if the mass of the star is not high enough, the outer envelope, the outer atmosphere of the star, can be shrugged off into the interstellar medium to form a planetary nebula. In other words, a nebula comprising the various elements that the star produced during its life. What's left behind is the original core of the star, which becomes simply a white dwarf, something about the size of the Earth. It starts off white because it's hot, and eventually it'll cool off and become a black dwarf. That same cloud of hydrogen on the left might condense and produce rather massive stars, let's say a mass with more than mass of a star with more than 10 times the mass of our Sun. That will live a shorter lifetime because it will need to produce much more radiation to balance the rather strong forces of gravity. It will only perhaps last for millions of years rather than billions of years. It'll end its life as a supergiant, and depending on the mass, it could end as a supernova. Again, shrugging off its outer layers, but this time much more violently rather than the rather slower slough of the planetary nebula produced by a smaller mass star. If a star goes supernova, what's left behind will either be a neutron star or a black hole, depending on the mass of the original star. But what's left behind, the white dwarf or the neutron star or the black hole, is only a small fraction of the original mass of the star. Much of the original mass is recycled either as a planetary nebula or as a supernova remnant, and most of the material, especially all of the elements generated during the star's life and possibly during the star's death, all of that material is recycled back into the interstellar medium and back into these clouds of hydrogen, which generation by generation become more and more enriched with these heavier elements generated by earlier generations of stars. And our Sun was born from such a cloud that had already been enriched with some of those heavier elements, which is why the Earth contains some 100 or so elements rather than just a few of the lighter elements. So when we look at the life cycle of stars, when we look at stellar evolution, we remember that a lot of our understanding, the details can be quite complicated, but the basic of our understanding can come from understanding the three factors that determine the life cycle, the A, B, C of stellar evolution. Thank you for listening.